Hello and welcome to another episode of Learning Rust with Good Oxide. Hey Sid,
Hey, Sebastian.
it's good to have you back. And we say hello to iterators again. Hello again to iterators and again, because it's not the first time we try to record this one, but today we will succeed. So what you see here is my attempt to do something that is as unusual as I could make it by trying to do something like a standard C or C++ for loop where you have some sort of counter that is used to index an array. So that's an array, that's not a vector, so that's statically allocated. It's immutable too, this one at least, because there's no mut anywhere here. And yeah, we print some numbers. So if we run this, it should tell us what's in there. All right. But since this has, since this does an indexing operation here, there's always the risk that you run out of bounds. So now I changed this range expression here to also include the length of the vector, and that will not be a valid index for, for v, for the value. That will not be a valid index for the array. And I think this is where iterators definitely come in handy, because what if we could just iterate over the values inside of the array? Because then this shouldn't be possible, because somebody else already wrote some loop that just works, which is great. And this is something we can do next. But also I think it's worth noting that this for in loop, that's the way you loop. I mean, that's the for loop. That's how it looks like. That's the syntax. You always have a for in. And this part of the in, I mean, I don't know. What does that look like to you?
Yeah, I mean, this range expression, right? I'm not really sure what it returns, but it could be something like a list or an array of numbers that then just gets, looped over.
Yeah, that's true. It's a range expression. And there's actually a range type. I think, yeah, I'm unable to use IntelliJ here to jump to that syntactical range that we have here. But it is indeed something you can look up in the standard library, and you can, I mean, if that was true, right, then I should be able to do this, and I should be able to do this as well. So let's see what kind of range that is. And yeah, it just printed itself, so to say, the way you would write it as a range literal. But there's more to that. I mean, you can have a start, you have an end, and maybe now we have a type that I can jump to. Yep, so that's a range, and it tells you all about it. Half open, inclusive, oh no, exclusive range. Okay, so end is not included in the iteration. Oh, I said it again, iteration. Yeah. So, I mean, iterators are at the core of anything that you loop over, or any kind of sequence of values. This is what an iterator is, a sequence of values. This can be generated, this can be known in advance. There's different kinds of iterators that represent different kinds of sequences with slightly different properties. And that's pretty cool, because now you open up the whole tool set of functional programming as part of using iterators. And the for loop is kind of the most clumsy way of doing things, because yeah, most of the time you don't even need a for loop anymore. Sometimes you do, but often, I mean, most of the time you don't. All right, so how do we write this as an iterator over the values of v? What's your suggestion?
You mean with a for loop, or
yeah.
with so can you just iterate over the actual array, so just v?
All right, I can. Oh, but I should probably adjust this, because now I use the value instead of v to index v, and now 1 and 2, these are lucky, and 3, it isn't. So out of bounds here. But that should be fixable. So now we just do this. And it's the same thing. It's impossible to get wrong. And this also has many benefits to do that, because now there is no bound check anymore. So the bound checks are completely deleted here, whereas previously there would be a bound check, right? It has to check that you're still within the array, which is of course slower to do that. So also something you would like to avoid. Okay, let's see. Yeah, I think the next step we can take is to make this a vector, because, well, maybe not. Maybe we can skip the vector part and just put something more interesting here, because I would like to explore next how the whole ownership thing works within iterators. And maybe from there we also understand a bit better what this for in really does, because getting a mental model for this really helps to, get by and understand what the compiler is trying to tell you when things don't compile, which is always great, because it's always real, something to fix. It's always something that helps. So, but not always easy to fix if you're new to this. So let's see if we can get some compiler errors or a better understanding. First of all, let's put something in here that is owned. Actually, let's be nice, do something nicer. So you see what I'm doing here? The first member of the array is an own string that I create explicitly. And the second member is now just using the inferred type of the array, because now we know it's an array of strings, and the compiler can now know how to convert something else into a string. And these static strings, of course, they can become a known string, no problem. And that's
pretty cool.
Yeah, that's neat. So now if I iterate this, what happens? 1, 2, I still see the values. Maybe use the debug print here so that it becomes clear that this is actually a string. Now with quotation here, nice. And yeah, can I do anything with that? Can I now push something onto it, a character maybe?
Probably not.
Because it's not mutable. Can I just make it mutable and it will work? Wow, amazing. That is a little bit unexpected, but I think it's something that was maybe recently added in the most recent Rust release, because previously it would definitely I don't think it would allow you to do that, because now we have consumed the vector, right? So if I now print or try to do anything with that vector, let's just get something from it. It tells you that it indeed moves here. So that loop is consuming our array, which is interesting. You would think it's kind of something static, but because it's an array, not a vector, right? This is in a location on the stack, but we are able to consume that allocation nonetheless. Okay. You look a bit puzzled. That's great.
Yeah, but I think it makes sense though. Like, of course, you use the value, or you use the value inside the array there. So yeah, there is no way for it to be in the old location. Essentially, it's a move. Yeah.
Yeah.
I think I get it.
The thing is, for you, it might seem more logical than to me, because I knew how it was before. And before that, I would always borrow these, I think. And this was because of some limitation that, of course, couldn't now reproduce or tell you more about, because, yeah, some limitation. Because this is actually, let's check the type. I think I remember now what limitation was. Let x be v. What kind of type is this actually? This is the type. This is the notation of this. So the first part before the semicolon is the type, and then the amount of things in there. So these are always homogeneous, as opposed to tuple, which is a sequence that is non-homogeneous, but this one has to be homogeneous. All right. So it is an array, but this is also its own type. So as you try to work with differently sized arrays, you will see that they don't really want to behave like, oh, we are all arrays. No, they're not. I'm an array with 2 things in it, and the other one is an array with 3 things in it, and they don't want to cooperate. Even though they're both filled with strings, but the one with 3, it's kind of a thing between them. And of course, this means that somebody, if there are traits to be implemented here for an array, somebody has to implement the traits. So if there should be an iterator trait, then this iterator trait has to be implemented for an array of things with 1, 2, 3, 4, 5, 6, I think up to 32. Up to 32 array size you could have, and then there wasn't an iterator anymore, something like that. Which is fair, you can work around that, but this is why this did not consume, because they couldn't make it work consistently because of this limitation. But now recently, the type system was improved, so it's possible to be generic over the amount of things in something. And that's this is why it can now be looking like, yeah, that's how it should be, right? It should consume. Okay, so how would I then avoid consumption? Like,
well, you borrow it in some way, right?
Yeah, I mean, if something would be borrowed, then I couldn't consume like that. This is what we know, especially if it's read-only. So I can borrow this here. So now it's a borrowed. Yeah, let's see what kind of type it is. Should just be a borrowed array of 2 things. It is. It's still not a slice though, right? Slices look different. Slices are just a sequence of things with any length. So basically what's behind here, behind the semicolon and the semicolon, if you wouldn't have that, that would be a slice then, right? But this is just a borrowed array. So still not much different, but already different enough to prevent this from happening. We should be able to mutably borrow this. And this mut isn't needed anymore because now we have mutable strings coming out of this thing. But also, that should mean that we can do this. Nope. Still consuming. That's a bit unexpected. But also probably okay. Okay. Fair enough. I just take it as it is. So we can apparently move out of this iterator, this loop moves out of the mutable reference here and somehow consumes it nonetheless, even though it never owned it, kind of, right? This is a mutable borrow, and you can do things with a mutable borrow. You can replace the memory in the mutable borrow, but then you would still be able to use it afterwards. So that's a bit strange, but maybe let's rewrite this. Maybe it's about the way we write this. So now let's make this mutable. Okay, so far so good. And vlang. Yeah, now it works. Now it works because now it knows that we just take a temporary borrow here, and out of that you can't move. So the v, the array in the v binding stays intact. But it's also interesting how this now played out, I find, because I didn't really expect it to happen that way, but also, yeah, I guess I can understand why. Now it at least still gives us v and doesn't take it out, which it shouldn't be able to do.
Yeah, I think it makes sense somehow, but I mean, yeah, technically it is the same type, so, but it matters where you declare it in the end.
Yeah.
But yeah, and probably that means, okay, so you first have it assigned to v, and then you say explicitly, okay, here, that's where I want to borrow it. And then it understands, okay, it's not actually a move. It can stay in place.
Yes. By the way, when I see this, somehow I visually feel that it pulls some semi-transparent thing out of that opaque own thing. And that's the borrow. You know, that's how it feels to me, like swoops, temporary, and it flashes back, it pulls back as you get out of that scope here. I don't know. Probably a lot of Rust does that to your brain. I always thought of Rust as this thing that forces you to, or the compiler forces you to get this little tumor in your head that is like a simulation of the compiler. So you can write some code without getting stuck all the time. So a mini compiler in your head, but it's still much worse than the actual compiler, I must say. So always trust the compiler. Don't think too much. Don't get that tumor. You don't need that. All right. Now, let's keep playing, I guess. But I think the most important thing to keep in mind here is that this will always try to take ownership. That's the default for loops. But you can also prevent that by just giving it a borrow of something, or by manually calling certain functions that you will always see on sequences, which is iter name, not this one. This was IntelliJ. Happens all the time. I wish I could deactivate that. That it makes a loop for you. So this should be the same thing. Let's remove the mut here. Let's remove this. So now I'm iterating over. What is this? Borrowed strings. Makes sense. Iter mut. Mutable strings. Borrows to mutable strings. All right. And by the way, something that seems like that's very implicit but super interesting. Remember the mutability rules, that a piece of memory that points to a thing can only be mutable, or can only be seen in a mutable fashion by one, well, pointer effectively at a time. But here we have a sequence of things. So in order to uphold that invariant, that only one item at a time in that sequence may be writable at a time and nothing else can be readable, you need to, you need to be very careful. You can actually, you can't just, you have to make an API that makes it impossible to reference multiple things at the same time mutably. And that's what iterators naturally do, because they only ever give you one mutable thing at a time, like this. And if you try to do this yourself, if you try to do this manually or try to implement a sequence yourself, you will see that in order to do this, you do actually have to bypass the compiler and say, look, listen, I know better than you. Trust me, this is the only thing of my sequence of things that is mutable right now. And this is also what's happening under the hood. Like a lot of unsafe stuff is covered up behind a safe API that is actually working. But yeah, not everything is perfectly provable at the compile time, so just saying. But I might digress. So let's remember iter and iter mut. That's important things to call, but most of the time you don't have to call them. Just try to iterate, and if that doesn't do what you want, or it's consumed after and you still want to use it later, you can of course just borrow it or mutably borrow it as a shortcut to iter or iter mut. And that works everywhere. Okay. Now, these iterators. These iterators, they are... And we can actually work with this array. This is very much like, this feels very much like a vector that has a heap allocation. It's pretty much the same thing. It's very consistent now. That's awesome. It's my first time to realize it's consistent. I think that will help me to write better code in future, especially when you write tests. It's, you know, I tended to use vectors because they were just less annoying and they just work as I would expect. But now I can just use arrays all the time and know it's fine. While also consuming things, like iterating over something in a consuming fashion, you know, having the thing owned that you iterate over is usually practical. It's you can do a lot more with it than having a borrow. So that's why I like to consume these when I iterate over them if nobody else needs them anymore and if I own them, right? So yes, consume them, be done with it. Also prevents misuse later if you don't intend to use it later. Things like that. So makes sense. All right. Then iterators. Iterators are over own thing. So in theory, I should be able to simulate this here using my own loop. Like, what is this really doing? Let's understand that better. So let's take it apart. So here is something that we get out of the iteration, and here is a thing that yields an iterator if we tell it to become an iterator. And we can do this by calling into iter. So into iter is a trait that is called into iter that you can implement on your own type. And this allows you to transform something into an iterator in an owning fashion. And now we have an iterator. And the major, it's interesting that it cannot see this. Yeah, what kind of type would that be? Can we see that here somewhere? Not really. Okay, well then we do it without IntelliJ's help. Why not? But I can tell you that there is one function that is important, one method that is important, which is next. So that gives you the next element in the iteration. And that yields an optional item. So an option string. And that is some string while there is something in the iteration, and then it's none exactly once or multiple times. But the first time you see none, you stop the iteration. And that's that. So in theory, we should be able to say, while let's destructure this here, while let some I, let's make this iter, while let some iter next, and we should be able to have exactly the same loop as before. All right. And now we also see that this iterator is allowed to mutate itself while calling next. So because it has state, it has to increment some counters, it has to do some bookkeeping in order to do a loop usually. And maybe there are some iterators out there that are just generating things that, you know, have some formula, but even then you always have to have state that tells you where to pick up next. And this is why mutability is key here for the iterator itself. But this does not affect the mutability of the underlying thing. You can iterate over immutable things. It's just the iteration state itself that is always mutable.
Okay, that makes sense, yeah. The iterator itself has to be mutable so it can update its internal things, and so you have to declare it as such, yeah.
Yes, makes sense. Then, where's this mut? We don't need that anymore. So now this is also, can I jump there at least? Yes, so you see this is consuming here. So that always pulls the thing that you want to iterate into itself, and it keeps it inside, uses it, and in some way or form throws it away later. You can't get that out anymore. That is now gone. But that is what the standard loop does. That's the one we have seen here. So this also means that here we have actual strings. Okay. And this also means that if I call this, let's see what happens if I call that again. So if I'm here, I've seen a none or not some. So now I call it again. Let's like, does it crash or does it give me another none? Okay, it does nothing. That's fair. So that's implemented in a way that allows it to do nothing. I think there's also a way to fuse it. And a fuse is literally that. It's a safety. So if there are iterators that crash or have great issues, if you call them again after they're used up, but if it's possible in code that this thing gets called again, you can just fuse it, which puts a fuse around the iterator. And that makes it safe to call, even if otherwise it would be crashing or panicking.
I see.
When I say crash, I mean panic, because nothing else is allowed in Rust. That wouldn't be considered a bug. And you see already here that these iterators, they have a lot of capabilities, even though IntelliJ can't really see that right now, unfortunately. But they have. You can, transform them into, you can wrap stuff around them one by one to add different capabilities. For instance, you could also make it peekable. So a peekable iterator allows you to call peek, which does not consume the next item. It's literally just, is there a next item? Tell me, but don't use it up. So you see, I saw one before I iterated one. But I can peek again, it will still be one. See? So I can only peek one item at a time.
Yeah, that makes sense. So you basically in these iteration steps, you work on one value and you do whatever it is you want to do. And then next basically ends that and goes on to the next value. Yes. But with peek, you can peek onto the next one without actually ending it. Yeah.
Yes. And this can be useful if you want to see if there's something inside the iterator at all, or if the next one would end the iteration in case you want to do some cleanup now. Or if you're basically would end the iteration, is kind of a weird thing to say that you are on the last item. Like this is the last item in the iteration. Maybe now it's time to do some cleanup of some sort. This is when you use peek. Or if you are a parser of some sort, then you have a look ahead of one item exactly. And that is usually enough to do most of the, or many parsing tasks. But that's as good as it gets. You only can peek one, but probably by looking at the implementation of this, you can easily implement a peek 2 or something and have a bit more look ahead if you want to. It's just about having more state to store these things that you looked at and then doing the state management to know, whatever. It's probably already been implemented by someone and there's some crate that allows you to do multi-peek of some sort. Yeah. But that's iterators. They're super, super powerful. So what if we wanted to change, add 1 to each of the, oh no, wait, we don't have numbers here. What if you wanted to modify the string a little bit, like before? Sure, I can do it like before by putting it here. But what about just changing the value on the fly? So here we have a string, it should be mutable. And then I definitely return the string, but I also want to push a character. What about this? And now I get 1C, 2C. As part of my iteration. And what if I would like to select the values that only, or that are, that are what I want it to be. So let's only do this on the one that is called 2, and everything else we ignore. Okay, now we effectively limited our iteration to one item. There's probably faster ways to do this, but a filter map we've just created here. And each of these calls obviously creates its own iterator. So it's a nested type. Each call gives you a new type as a wrapper around the previous one. Which means that, of course, we can print the type, right? So why not? So we have a map filter array into iter. And one of these also has a closure here that has this type. So closures also have a type, but it's something you can't put into a structure or anything like that. I mean, you can't store it because this type is undescribable, at least statically undescribable by nature. You can generically handle these closures, of course, but yeah, let's talk about that in a separate session. It's worth it. But yeah, it is a big, long type, and of course that just gets longer and longer the more cool things you do, but no problem there. It's possible to kind of create types that are so large that you get slight issues with memory or type depth, and you have to increase some values in the compiler to do that. But it's usually auto-generated types that get there and not your puny little iterators here. Yeah, but that's iterators. So we have into iter, mud. And can I still do this here? Interesting. So if I just want to iterate over borrowed strings, things look a bit different because I also want to mutate later. Does that change it? Interesting. So this does not work anymore. Maybe fix all of these one by one. And it does not work because now I have a borrowed string here and I want to compare it with a string slice.
Oh.
And comparison is not necessarily implemented for all the different inputs that you can see. Usually what you do is look at what it suggests you. The trait partial equality for string is not implemented for a mutable string or for a double reference. So I think that's the problem here. Look at that. So here it looks like it's a single borrow, but actually we have a double borrow. So we have a borrow to a mutably borrowed string.
So you dereference S in the filter?
Yeah, I do that. And you would say, why is this doubly borrowed here? But that's the filter. If you look at what the filter does, yeah, well, it's probably a bit hard to jump to the implementation. Let's see, because these things can be complex and, you know, I think I don't want to try to find the implementation of this. But let's just say it just borrows what it gets from the input iterator. So it gets whatever this would output, a mutable borrow, and then puts another borrow in front of it, and that's it. And this is why you have to dereference this. There's another way to dereference this which is to destructure it. So you can have a pattern here on the left side, actually. And I can say, please match me, which to me is like take away one of these. Oh, doesn't work? Okay, let's see why this doesn't work. Data moved here, moved because S is type mud string, which does not implement the copy trait. Okay, so we can't do this here. Because it's a mutable string. If this was an immutable one, these can copy. But this can't copy. Interesting. Yeah, so here we do have to deref. But if this was an immutable iteration, then we can also do this and structurally match away. I don't know how to even say that. One borrow. But I think it's easier. You know, I use this, I must say I use this never. I always dereference. Probably because dereferencing is less
confusing.
Yeah.
That is definitely more clear, like the dereferencing thing, to me at least. I mean, if you get
Yes.
used to it, maybe, but yeah, the other one is kind of backwards. Yeah.
Yes. Something, yeah, it does make sense. It does make sense too, to always borrow when you are filtering. That's fine. Okay. And the mapping then does have what comes out of the itemat, because the filter just, you know, lets you look at something, but then decides whether to pass on that something or not. So if you see it here, it's just what came out of itemat. And the mat here is not needed anymore, because within the s binding, there is a mutable string already. And it's not own anymore, right? It's just a mutable borrow. And that's that. Iterat. Okay. So iterators are quite practical. And I wonder if there, you know, if there's anything more confusing to this that we should talk about, because we have been talking about 35 minutes already, so maybe another 5 with the cool stuff. What could be cool?
Yeah, I do have one question, or maybe just something to talk about. I mean, I know coming from TypeScript, you know, you usually use these iterator or these array functions to modify an array, right? So you put in an array, you filter it, you map it, and then out comes another array. But here you have this weird type of a mapped filter over this array that is kind of turned into an iterator. In the end, I guess it doesn't really matter, but like, where's the output, right? I do want the values back at some point, because that's probably the point of doing the iterations.
Where's the output? Great question, because we never really talked about this. Yeah, let's just check where the output is. Hence, I print the value here. Yeah, debug here is also consuming. So I kind of naturally put an ampersand in front, but we don't care, really. It can consume it. We don't use v anymore. So that's interesting, huh? Because we did have the filter, we only mutated on the fly the two, and the first one is unharmed. So yes, iter and itermat always borrows elements in the underlying sequence. Therefore, that's what you operate on. So if you mutate stuff, it mutates them in place. I think that's the key also to high performance iterations and high performance mutations, in sequence anyway.
Yeah, so you do have to be pretty careful when you borrow this stuff, or be really aware at least. And I guess, yeah, that's why by default it just consumes it, because then you know exactly what's coming out at the end.
Yeah. I mean, with the consuming, I mean, as always, it's kind of in your face whether something is mutable or not. But anything with _mat might be a bit less in your face, because it's not really syntax anymore, right? It's not mat that is highlighted. It's just some part of a function name. However, it's also the longer version of the two, so it's something you don't usually accidentally do that easily. And also, yeah, you will be alert when you see mat, and probably accidental mutation doesn't really happen. Never happened to me, because there's so many things that don't work with mutable stuff that when you have mutable things, you always have to be extra. The compiler will often stop and tell you that things can't be done, and then you will probably see the mistake at the latest. But at runtime, oh, I accidentally changed something at runtime. Never, ever. Doesn't happen.
Yeah.
I can tell you, it doesn't happen. Never happened to me, and I probably made all the mistakes that are in the book, that are possible. So mutation in place, and with into iter, then of course, yeah, you can do what you want with the element, and whether you store it somewhere else or do, I don't know, whatever with it, that's up to you then. But doing it like this has huge advantages. There is, of course, always the question of how do you iterate something that you want to mutate as well, but maybe mutate on demand or mutate conditionally. Well, this already is one version of that, right? This already allows you to do a conditional mutation. But often, you know, when there's one reader that just wants to iterate stuff and another writer, you can't have that in Rust. So if you have these kind of things going on and this happens in real life code that you want this kind of thing, you always need to have some sort of extra buffer that takes the edits that are then later put into the right place or something like that. Maybe there's also a final note, because I believe I do remember where I did exactly that not too long ago. So there is this thing here. There is an edit for publish, which is exactly that. I have to iterate something that I also want to edit. And because of the nature of this iteration, because it's a dependency graph, it's a recursive thing. So then you can't just iterate mutably anymore. Because then, you know, there's one part of the recursive function that has, do you see that recursion here? Let's see. Because it would highlight that here as well. But depth first traversal. Yeah, it doesn't highlight the recursion, unfortunately, but here it is. And when you have this, then the borrow checker will basically just say no to you. And in order to still be able to make certain edits, what I do is I store these edits with enough information to apply the edit later. And you see here, there's an index into the array and the kind of change that I want. And that's all in this case. And then you just apply it once you're out of that situation where the borrow checker will not let you have multiple writers into the same thing at the same time, which is fair. And that's the alternative. That's the Rust way. But also it's the safe way, because I think you bypass so many potential bugs in the process, like the kind of complex stuff that you can do in Rust, because it forces you into patterns like this that are actually safer and easier to implement. It's a bit ridiculous, because it is extra, but it's the better way to do things, and it's not less performant either. It's amazing. And, you know, maybe in 2 years when you look at it, you are able to rewrite this as some sort of mutable loop over that, and like we just did, maybe sometimes you don't see these opportunities, but I believe I didn't miss it here. At least right now I do. But that's one way of bypassing this, and usually that's how it's done. Oh, by the way, I have to say, when you have this kind of situation where you want a portion to be readable and the other portion to be writable, then sometimes it's just a matter of data structure. And I'm one of the people who probably just knows two things as data structures, which is vectors and maps or sets. You know, these three things. It's three things. Yes. But there is also a vecdeck, and a vecdeck is it's a continuous sequence of memory, like a vector, but it has a midpoint. And with that midpoint that can move around, you are able to pop something on the front and push something on the back. Like, you know, it can grow on both ends, so to say, like this. And with that, you can actually have or read one end and write to another or something like that, because that API is specifically made to allow that kind of thing. because it's possible to safely do that. And if you express your algorithm in terms of a vecdeck, you save a lot of complexity, and things will just be the way they always wanted to be. And I have such an example as well here in Delta Traverse. So let's see into items. If there's something that makes any sense, like where are these items written? If you can see how this is actually used. Yeah. Anyway, this vecdeck push front, this has this fantastic property. Where is that fantastic property? Is that somewhere here? It's a bit hard to see, but the code before didn't use a vecdeck, and it was super complicated. It used unsafe a lot, and I was told that this is also non-proper use of unsafe, which is immediate undefined behavior, which is kind of the worst slap you can get in the face as a Rust programmer, because that's usually what you don't get and do in Rust. And if you use unsafe, you better know what you're doing, because yeah, and I did not, and I tried my best, not good enough. Anyway, some person came along and made this into the vecdeck and removed a lot of code, and it looks so much better now. And that's when I learned that vecdecks have this fantastic property of allowing you to, you know, do different things with the both ends that you have. And that was fantastic. And maybe I explained it all wrong now, but now whenever there's something that allows that is different kinds of things, maybe different queues, 2 different queues in one, something like that, then I use a vecdeck, and I know that's the better way of doing things for the algorithm. Yes, vecdecks. So now I know 4 things. Okay, I'm off by 1, but what?
It's probably a lot more.
Yes, I mean, yeah, maybe. I mean, there's also queues, and just look into std collection. Std collections, this one here, that has a lot of nice things that you should probably be aware of. But a vecdeck, I knew that before, like by name, and also kind of what it is supposed to be, but I never knew how to apply its capabilities to my problems. But I think now now I might be able to use it. Let's see when I actually get to use it the next time. Yes. Let's close this up and see what there is. Is there anything else with iterators or for iterators? Yes. One more thing, maybe. Let's see if we can have this here. Let iterref be iter by ref. Okay, because this iterator, you can only use it once, right? So once this is consumed, it's gone. Like the iterator itself is gone. Let's make this an element. Let's see what this by ref does, or if this does anything useful. Let's keep iterating this iterator. Can we do this? Yeah, okay. So now as I run this, we get none. Let's see what we get from iterref. Let's see, I don't actually know. Oh, look at that. It doesn't like that. Because that is a reference, that is an iterator over the borrowed iterator here, by ref.
Just mutable.
Which is mutable. So the mutation seems to be part of the problem. Let's remove it. But it's still part of but still an issue here, because now we can use this for iteration here and then later use the other one. Let's see. Okay, see, it's all about order.
Mm.
Because now, once we stop using, or if you don't use iteref later, it knows it's basically gone, and we can just consider this done, and then this is free to move. So let's see. Yeah, but we did consume both in the process because one is a reference to the other. It's interesting because I was able to use byref sometime effectively, which was like, what is byref actually doing? Borrow an iterator rather than consuming. It is useful to allow applying iterator adapters while still retaining ownership over the original iterator. Ah, that's why. So
Iterator adapters, are these like filter and map and stuff like that, these methods?
Yeah. So it's more like a pipeline, a selective pipeline or something like that. So we can have one version of the iterator here that doesn't have the filter and the other one that does have the filter. Maybe. So let's try this to use this somewhat effectively, at least for once. So here we have a bare bones iterator, and here we have a referenced iterator that has a filter. Okay. And maybe also put a third one in there so we don't run out of items.
Oh, I see. So you could potentially switch the iterator. No.
Yeah, you can. That's the thing. So now you can make a temporary iterator that has a filter or other properties that the original doesn't have. They will still, this one uses, this iteref uses iter, right? So what this one here consumes will not be seen again also by iter, but I can have different properties for my iteration. So now I would assume we see 2 and 3, skipping 1, because first time iteref skips 1, sees 2, is happy, and then we use iter to see the third one, which is unfiltered. So if you would call iteref again instead, we would see nothing anymore because this one only wants to see one particular item.
Okay.
And this is exactly what byref is used for. And now that we slowly get a bit more into relationships to get oxide, let's see where byref is used. Okay. Ah, yeah. So here we have an iterator over events. This is parse events for a markdown file. And there's a top level iteration where we just iterate over everything. But then sometimes, depending on what we saw there are sub iterations that have a filter. So take while this is true. And this is why I take events by ref in order to be able to have my own little special iterator that has different properties, like a filter. And this is how
so
you
it's
would
essentially a complicated skip, right? So you're really just skipping over values that you don't need, and you can build that with your own or with a separate iterator, which is really powerful.
Yes. So essentially an iterator, especially when you're parsing something, this is probably one of the standard use cases. Like here, you have parsing events and you would see any event, but depending on what you see, you now want to have different kinds of iterators to parse more effectively or parse differently the next section that you now know how to expect. And then you drop back to your original iterator where you keep parsing by hand, one by one, just to build some more specialized iterator the next time you see something else. And that's pretty cool, very powerful.
Yeah, so you go from a coarse iterator to a more detailed one for for specific things that you cool. That sounds useful.
So whenever you consume your iterator by accident, just use byref, and then you get your referenced iterator and can work with that differently while dropping back to the original, which never went away, right? It's just something you can't use while you use the reference for obvious reasons, because this one is being mutated under the hood. So this one is unusable. And that's also cool, by the way, in Rust. Rust could tell you, no, I don't want to do this. But you can temporarily shadow also mutable references. As long as you don't use this one, you can use this one. And then as this goes out of scope or becomes otherwise unusable, you can use the original one again, because that now is not borrowed anymore. And that's just that. It's a borrow. Yeah, borrows automatically snap back. All right. That might even be it about iterators. It's a trait, so you can use that as well to be more generic over things, but we'll talk about generics another time. But I think that's pretty much it. Yeah, that's all I know for sure. All right.
It's a lot. Good.
It's a lot, and that was a long session, an hour nearly. So thanks a lot for watching, and everybody have a nice weekend. Bye-bye.
Bye.